Hello, my name is Manoj Choudhary. I'm a senior technical staff at Owens Corning's Science and Technology Center in Granville, Ohio. It is my pleasure today to say a few words about a review article that Professor Matthew Hire of Virginia Military Institute, Dr. Raj Venuturumili of ANSYS Incorporated, and I published in the June 2010 issue of the International Journal of Applied Glass Science. First, I want to thank Dr. David Pye, the editor-in-chief of that journal, for inviting us to contribute the paper. And I also want to thank him and Hope Inman, editor of Wiley, for asking me to prepare this video abstract. The paper that we are discussing today is Mathematical Modeling of Flow and Heat Transfer Phenomena in Glass Melting, Delivery, and Forming Processes. In this article, we present a comprehensive review of computational fluid dynamics-based simulation of industrial scale glass melting, delivery, and forming processes. We also present a historical perspective on the development of CFD-based tools and their application for glass manufacturing. We present some results to illustrate the capabilities and limitations of these tools. And finally, we identify a number of areas that need research and development. The CFD-based modeling in the glass industry began at a sort of rudimentary level in the 1970s, but especially in the last decade, it has become closely integrated, at least in the large glass companies, with the design, operation, and in some cases, control of the glass manufacturing processes. So let's briefly talk about the three blocks of processes, namely melting, delivery, and forming. And each of this block consists of complex and often mutually coupled sub-processes. So in the melter, we have the melting and dissolution of raw materials, and we have flow and heat transfer in the glass melt. The flow is typically caused by thermal natural convection. In addition, one may also have convection due to forced bubbling. By forced bubbling, I mean bubbling that is used to homogenize the glass melt. So this is on top of or in addition to the bubbles that may already be generated in the melt associated with the melting phenomenon. The source of heating for the melting, could be electricity and or combustion in a combustion chamber atop the glass melt. In specialized cases, one may also encounter plasma melting, microwave melting, and some other means of introducing energy. In some cases, the combustion, rather than taking place in a combustion chamber in the top part of the furnace, combustion may take place in the glass melt itself. The design criteria that the melter has to satisfy will involve supplying at a consistent rate, given quantity or given throughput of chemically and thermally homogeneous glass to the delivery system. The delivery system consists of usually a network of refractory channels which transport the glass melt that is produced in the melter to the forming machines where the final shapes are made. The phenomena in the delivery system are somewhat less complex than those in the melter because, first of all, we don't have melting and dissolution taking place in the channels. Also, the geometry of the delivery system is typically simpler than that of the melter. Now, depending on the different segments of glass industry, whether one is talking about container, TV panel, flat glass, fiberglass, the design of melters and delivery system, although they can look different, they share many common features. So it's not surprising that most of the attention to modeling has been given to the melting part and then to the delivery part. When it comes to forming, however, depending on whether one is making glass fibers or glass bottles or tableware, or TV panel or sheet of glass, these processes can look very different. Broadly speaking, however, we can divide the forming processes into two groups. One group involves forming discrete gobs of glass and then pressing it into some final shape. The other broad category of forming involves continuous supply of glass being shaped into final form, like fiber or tubes. So in the case of melting, one deals with Navier-Stokes equations, and in the paper we provide the basic scientific and engineering concepts and equations involved in modeling of this phenomena. So in the melter, one has Navier-Stokes equation with allowance made for different sources of convection. As I said earlier, thermal natural convection. In addition, one may have forced convection due to bubbling. In those cases where one has combustion taking place in a combustion chamber on top of the glass melt, to model the combustion phenomena, one would require Navier-Stokes equation written for turbulent motion. And of course, one has to couple the equation of motion to equations representing combustion phenomena, combustion kinetics. And because the flow is turbulent, one also needs engineering models for handling turbulence. So that can be done, for example, by using the so-called two equation models of turbulence involving turbulence kinetic energy and the dissipation rate of turbulence energy. In the case of 4-hearth, maybe I did not mention that, the section of the channel, the delivery system, that is close to the forming machines, that is often called 4-hearth. So in channels and 4-hearths, the source of energy is typically, again, combustion atop the glass surface, but in some cases people also use electric heating to provide heat in the bulb. The design criteria of the 4-hearth of the delivery system, of course, is to deliver, again, on a consistent basis, glass at a given throughput level, that in addition to being chemically homogeneous, is also, as much as possible, thermally homogeneous. The transport equations for 4-hearth, again, will be Navier-Stokes equations, and since we are dealing here with glass melt, both the melter and the 4-hearth, we talk about the laminar flow. And if we have combustion phenomena taking place in the 4-hearth, then just as in the case of the melter, one needs to model the combustion phenomena in 4-hearth as well. Now, our paper had already become pretty massive by looking at the melting and delivery processes. And we were thankful to Professor Pai for being so generous with us, but we did not want to misuse his kindness, so we confined our attention to one kind of forming, namely container forming. And in the paper we have the transport equations relevant for container forming. And incidentally, in each of these 3 major blocks of processes, namely melting, delivery, and forming, we have included constitutive equations and also boundary conditions. Now, unlike melter and channels and 4-hearths, in the forming, one cannot typically ignore the non-Newtonian nature of flow. So melter and the delivery system can be handled by using Newtonian concept of viscosity, but the flow phenomena in the forming processes will have to take into account the non-Newtonian nature of the flow, shear thinning, for example. Also, in some parts of the forming process and modeling of that, one has to incorporate viscoelastic phenomena. I mentioned earlier that the melter has received the maximum attention. One of the reasons for that being is that that's a part that is common to various segments of glass industry. The next in the order of priority has been the delivery system modeling, and serious work in that area only began in the 90s. And forming is even more recent than that. So in the paper, we give results illustrating the application of CFD-based modeling in the melter for the delivery system, and we also present a series of results for container forming. I would say that one of the most important sections of this paper, this article, is where we discuss some of the challenges that remain in this field. I do not have the time to go over them in great detail, but I'll mention a few of them very quickly. In the melter area, batch melting, even though it has become a lot more sophisticated than what it used to be in 80s or 1990s, we still have a lot more work to do to have a proper representation of physico-chemical phenomena associated with the melting of raw materials. Models also need more sophistication in incorporating phenomena associated with the foam that occurs on the glass melt surface. A lot of attention has been given to the formation of foam, and attempts have been made to incorporate the impact of foam on the efficiency of heat transfer between the combustion chamber and the glass melt, but a lot more work needs to be done there also. And of course, when we are talking about modeling and simulation, it doesn't matter if we are talking about melting or delivery or forming or glass or some other kind of materials process. You always need to have more rigorous validation of the models. In my view, that goes without saying. In the case of delivery system, I would say that considerable more work needs to be done in linking the phenomena in the forehead to those in the forming. That's an area that really demands serious attention, because this has implications for the quality of the product that the manufacturers make. I would say that in the case of forming, besides several technical things we have pointed out in the paper, from a practical point of view, the most useful advance that can come is if we can use modeling in a sort of reverse engineering way. By that I mean the following. When we do modeling in forming, we model the impact of operating conditions and design variables and see what impact changes in the design and operation variables have on the products that are made. It will be very helpful if, knowing what the product attributes are or ought to be, if modeling can be used to define what the design and operation parameters should be. I think that will go a long way in making models, glass manufacturing processes even more effective than they have been. So in the paper, we have many areas that we have identified for research and development, both from fundamental scientific engineering point of view and from practical manufacturing point of view. Let me conclude by saying that certainly in the past 3 decades or so, computational fluid dynamics-based simulation of glass manufacturing processes has come a long, long way. Starting from a fairly rudimentary level, as the significant advances took place in computer hardware and software that we all are quite familiar with, the sophistication of these models have become very high, to the extent, as I alluded earlier, that in many companies, especially large companies, CFD-based modeling has now become an integrated part of design and operation of these manufacturing processes. When it comes to control, some more work needs to be done, but great strides have been made in using CFD-based simulation approaches for advanced control of the glass manufacturing processes. With the area that we have identified in this review article for the 3 sectors of melting, delivery, and forming, modeling will go even further than it already has. With that, I conclude this video abstract, and I want to thank you for listening to this video abstract, and I want to thank my colleagues on this paper, Professor Hire and Dr. Venaturu Meli. And once again, I thank Dr. Pai and Hope Inman. Thanks.